Hello everyone! Today we will be talking about Chemisorption and Physisorption. These techniques are used to characterize the surface area and porosity of various materials. Let's introduce important definitions first. Adsorption is the process of adhesion of molecules to solid surfaces. It plays an important role, for example, in heterogeneous catalysis and membrane separation. We can distinguish two types of adsorption, chemical and physical one. Adsorbate are the molecules adsorbed on the surface of analyzed material. Adsorbent is the solid material that is being analyzed. Physical adsorption or Physisorption is a non-specific intermolecular interaction between adsorbate and adsorbent. Formation of only weak, non-specific bonds between surface and adsorbate occurs, and the process involves weak molecular interactions such as van der Waals forces, London dispersion forces, or interactions between dipoles. The adsorption energy is lower than around 40 kilojoules per mole, and the activation energy is around 0. This process is fully reversible and multi-layer formation is possible. Chemical adsorption or chemisorption is the formation of chemical bond between the adsorbate and the surface atoms of the solid material. It is usually an exothermic and very specific process and can be viewed as a chemical reaction. The adsorption energy is higher than the 30-40 kilojoules per mole, and the activation energy is non-zero. The process is usually irreversible and no multilayers are formed. In this video, an analysis of Physisorption will be performed, so we will focus on this phenomenon. Based on average pore width, 3 pore types can be distinguished: micropores, mesopores, and macropores. Adsorption differs for different porous materials. Microporous materials have significantly higher interaction potential than meso- and macroporous ones. That means that more gas molecules will be adsorbed by systems with micropores at a given pressure. The mechanism characteristic for micropores is the micropore filling, which is essentially filling of the volume of the micropore with the adsorbate. For mesopores, there is a hysteresis loop present in the adsorption isotherm that can be attributed to capillary condensation. Adsorbate condensation takes place in mesopores that causes shift in vapor-liquid equilibrium in the pore compared to bulk fluid. On the adsorption isotherm, the sharp step between numbers 3 and 4 is caused by the capillary condensation. After that, the pore is filled with the liquid form of previously gaseous adsorbate, separated from the gas by a meniscus. Desorption in this case proceeds by thinning of the meniscus. Point 6 on the isotherm is the point where equilibrium between the adsorbed multilayer and gaseous adsorbate in the pore center is reached. In macropores, the adsorption happens on the pore surface. This is because of the relatively large pore size that also makes mapping a detailed isotherm practically impossible. Other factors that influence the adsorption behavior are the shape of the pore and nature of adsorbent. The output of the analysis are adsorption isotherms. They show the amount of molecules adsorbed by a pretreated, so initially clean, solid surface at constant temperature and equilibrium pressure. For every pore size, different isotherm behavior will be observed. On the y-axis, the mass or volume of adsorbate normalized to standard temperature and pressure, STP, is expressed. On the x-axis, dimensionless relative pressure, ratio of pressure at which the measurements were made to the saturation pressure at the temperature of analysis, is expressed. Different types of materials have different isotherms, which allows us to differentiate between them, for example, based on the Brunauer classification. Let's have a look at some examples of the isotherm types you can encounter. Type 1. Adsorption in micropores, usually observed on activated carbons and molecular sieves, so porous materials that can separate molecular dimension particles. Type 2 and 4. For type 2, multilayer physisorption takes place, either on non-porous materials or those that have large pores. For type 4, additionally, capillary condensation in mesopores is present. Type 3 and 5. When interaction between the molecules of adsorbate is stronger than that between the adsorbate and the surface of the solid, so the adsorbent. The techniques can be used in applications that require information about a solid, including size, specific surface area, and pore structure. For example, analysis of Physisorption or Chemisorption might be important in the process of preparing catalysts, but also when characterizing materials used in chromatography, fluid transport, and gas storage. Start with weighing the empty tube and its cap that you will be using in the analysis. Then, weigh the substance and put it in the glassware. Also, note the overall mass of the tube with the sample. Transfer the tube to the pretreatment machine. You can use either gas or vacuum for pretreatment. This way, the surface will be clean and ready for the analysis. After pretreatment is finished, transfer the tube to the cooling compartment. When the tube is cool enough, weigh the glassware containing the pretreated sample. This is done to ensure you have accurate data on the mass of the substance that is an important parameter for the machine. The machine we will be using is Micromeritics Freeflex. It can take 3 samples at once. It is important to know which sample corresponds to which one of the numbered ports. Before you start the measurement, it is important to fill the small container, part of the machine, with liquid nitrogen or liquid argon. Put the vessel back in the machine. Transfer the glassware containing the material to be analyzed to the machine and attach it to the port. On the computer, check if the setup is programmed correctly. Open new sample file, enter its name and correct mass. Start analysis. The result of the analysis will be an isotherm that you can assign to one of the above-mentioned types. This way you can learn what type of a porous material your sample is. For example, looking at this isotherm, we can easily see that it belongs to type 1 isotherm. Thus, we can conclude that the sample contains micropores and might be a molecular sieve. From this isotherm, we can also calculate surface area, pore volume, and pore size distribution for this microporous material.